Hello everyone. So today we will try to apply naive Bayes method to the same loan default dataset. Okay, so let me first load the library. Now let me get the data. This is the data. Okay, again this time also we won't be doing any train test division. I'll be applying the method directly on the entire dataset, but similarly it can be applied to the cross validated data or the train test divided data. Okay, so now I want to decide the distribution of each variable. So for student we know we will have to take Bernoulli distribution. So let us try to draw plots of others to see how the other variables are distributed. So plot density of D dollar balance and then income. So this looks okay. I mean, I could approximate it pretty well via normal. There is not too much of skewness in it. Okay, then I will also try for income. Okay, it looks slightly bimodal, but again not very highly bimodal. Yes, ideally perhaps we could model it as a mixture, but we won't go there. So this one of the reasons for this could be that right now I'm plotting it for the entire data. We could try plotting things for the subset. So yd is d subset of d. So let me create the subset d, where d dollar default equal to yes. Okay, and then I could repeat these two things on yd and then on nd. So plot of density of yd dollar balance. Okay, the data has not been subsetted properly. Perhaps yes has to be capital. Yes, the variable yes has to be capital. Sorry, the value yes. See, this looks pretty normal. Okay, let me go back to the d dollar balance data. Here it was not looking that normal because this was combined, but now within the yes group, that is within the people who have defaulted, this looks normal. Let me try income. Okay, this is still slightly bimodal, but the second peak has slightly reduced. We will create the same plots for nd, that is no default data. So I can simply make it not equal to yes, and then check plot of nd dollar balance. Okay, and then plot of nd dollar income. You can notice that these plots for nd look more like the original data because that's the dominant class. Okay, majority of the observations are coming from that class. Okay, but as I said, as of now I'm going to assume normal distribution for each of these two variables, Bernoulli distribution for the student status, and then we'll try to apply naive Bayes. Okay, so I need to have a function which could give me probabilities of each of these three variables for each class, the yes class and the no class. So first let me try it for yes class. So let me call it y probe. So this is going to be a function of some input x that we give. Okay, so x is going to be the new observation. We will give it in the same sequence as the original data. So in the original data we know the sequence is student, then balance, then income. Okay, so we will follow that same sequence. So first for student status I need to estimate the success probability. So p1 I could call it P also, because anyway outside the loop I won't be using it. So P equal to length of which YD dollar student equal to yes divided by n row of YD. Correct. Out of all the variables, how many, sorry, out of all the observations, how many have student equal to yes? Let me run this. So this is my success probability for Bernoulli. Okay, 0.38 in the Y class, yes class. Now similarly I need density. For that I'll need estimate of mean and variance. So mu for balance is going to be mean of YD dollar balance. Okay, it is this. Similarly I'll need sigma for balance, so I'll call it SD for balance. SD for balance is SD of YD dollar balance, and I would compute similar values for income. So mu for income and SD for income, it is mean of YD dollar income and SD of YD dollar income. Okay, now given a new observation, it's F1, the first component is going to be Bernoulli probability. So Bernoulli PMF I will get by D binom x at 1 comma size equal to 1 and probe equal to P. Okay, we will try running every line of this for some x, and then things will be clearer. Similarly I will need univariate normal PDFs. So F2, or I could call it FS, that is student, then FB, that is for balance. So this will become D norm x at 2. Then I need to give mean and standard deviation, so I'll call it mu B comma SDB. Okay, and then I would have Fi. Okay, Fi will be D norm x3 mu I SD I, and product of these three will give me Y probe. So Yp equal to Fs into Fb into Fi. Okay, let me run this for say first observation. So x equal to D first row and column number 2 to 4. Okay, because I don't want to take the response variable. So let me run each of these lines. Okay, now let us see. X1 is student status no, so I cannot simply take that here. I have to convert it to 1 2. X2 is balance. Okay, but let me check class of X2. Class of X2 is data.frame. Okay, so I told you long back that sometimes this tibble business causes problems. So let me take this X as unlist. Okay, so I will define X as unlist this, and then I'll also convert it to numeric, and let us see if no gets converted to 0. Okay, let me now print X. So okay, so student status was no, so no has gotten converted to 1. Okay, and let me try what happens if my student status is yes. Okay. By the way, remaining things are, let me check, remaining things are okay. Okay, so what happens if I have student status yes? So let me check which D has student status equal to yes. So WY is which D dollar student equal to yes, and let me just print first entry from WY. Okay, so row number 2. So let me try this 2. So D2 is student yes, and this balance and this income. Now if I take this X, then how does it convert? It takes 2. Okay, so for yes it is taking 2, and for no it is taking 1. So but for Bernoulli we need 0 and 1, so I will subtract, so that for no it will become 0 and for yes it will become 1. Okay, x1 minus 1, and here I will first take x as this, as dot numeric whatever original x was, as dot numeric unlist x. Okay, so that we can pass on each row and get the outcome. Okay, let me save this file. So what we are doing, naive Bayes. Okay, so whatever we did for Y probe, we have to do similar thing for no class. Okay, so I'll call it N probe. This remains the same. Instead of YD I will have ND now, N row of ND, then ND, 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 fine, nothing, and this I will call as NP, and of course I have to return that. So here I have to write return YP, because that will be the output of my function. Here I have to write return NP. Okay, and prior probabilities I will get easily. So pi y, prior probability for y is n row of yd divided by n row of d, and pi no is 1 minus pi y. Okay, pi y and pi no. Okay, so now I have to compute px for every observation. So for I in 1 2 n row of d, let me create a blank vector px. So I will compute only probability of belonging to yes class, no class will be 1 minus that. So px numerator will be yes class, so pi y into y probe, correct. I have not run the loops, right? So sorry, the functions, so I have to run the functions so that the names will be available to me. We are running the functions, so it is taking some time to run. Ideally it shouldn't take that much time, but for some reason my PC is running very slow, so it is taking a time. Okay, see the functions have run. Now we can use those functions. Okay, so we have numerator as pi y into y probe, yes probability. Similarly, I'll define denominator. For denominator, I will have this numerator plus pi no, okay, prior probability for the no class into no probability computed via the function that we have defined here. Okay, we input x and get probability of no class, that is default equal to no. Okay, and my px for ith observation is defined as px num divided by px den. Okay, so pxi is actually probability of ith observation being assigned class I, being assigned class y, that is yes. Okay, it's running 10,000 times, so it is taking some time. Okay, it's done. Now to get predictions, I'll have to assign some cutoff, and then above that cutoff we will allot the class. So right now let me try with 0.5. So we will predict class as yes if this px is greater than 0.5, because it is probability of yes class. Okay, so if else px greater than cutoff yes, otherwise we will predict it as class no. Okay, so this gives me predictions using naive Bayes with cutoff 0.5. Okay, now if I want to calculate accuracy, we create this table. We can see here these 9615 are correctly predicted as no, 92 are correctly predicted as yes. These 241, they are actually yes, means actually those people have defaulted, but prediction for them is no. It means they are false negatives, and 52 are false positives. Okay, if I change the cutoff, then what happens? Our counts change. Okay, you can see false positives have increased. If I make cutoff 0.9, I get no prediction as yes, so 0 false positives. Okay, so depending on the cutoff, things will change. You can actually use different cutoffs to get sensitivity, specificity, and then use those to get an ROC curve for naive Bayes. One important thing I wanted to mention about naive Bayes is the naivete of this method does not become a hurdle. Okay, so even though the method assumes independence when in reality there is no independence, the performance of the method remains more or less quite good, reasonable, even when the regressors are known to be dependent. Okay, so that is actually an advantage of this method, that because of independent assumptions, computations are simplified, but still it does give decent results. Okay, so homework is try to draw all 4 curves for this data, default data, on the same graph, ROC curves for LDA, QDA, logistic, and this naive Bayes, and see which is the best classifier for this particular data. Okay, of course you will have to choose the individual cutoffs by looking at the individual ROCs first, and then compare and decide which one is giving you best performance, at least on the entire data. Okay, let me stop here. Thank you.